This unit connects really closely to the activity that we did on 4.4 of where you matched all the cards. This is the same idea, but actually getting into using that logic and sketching graphs and looking at how they're related. So if we think about all of our functions, if you look at a function, you can find the zeros, and those will end up telling you the y-intercepts. Right? You can factor it, find the x-intercepts. The derivative can tell you the increasing or decreasing behavior, as well as to help you find the critical points via, or find the local minima and maxima via the critical points. And then lastly, the second derivative lets you know concave up or concave down. I said those backwards. So this one's concave down, this one's concave up. And then it also lets you find your inflection points, which will typically look something like this or something like that. So by using all of these together, we can sketch graphs just from knowing details about the derivatives or the second derivatives. So in this first example, we're going to try and sketch a graph that satisfies this information. So there's local maxima at x equals plus or minus 1. The function is concave up for all x, and the function remains positive for all x. So I'm going to need my graph here. I don't need to go into the negative because they told me it's all positive. So this will be my x and my y at x equals minus 1 and plus 1. And plus 1, we have local maxima. The function is concave up for all x, and it remains positive. So we've got local maxima. So I'm just going to sketch in some local maxima. If it's concave up, that means we need to draw smiley face type structures. But if it's going to be concave up, that means it has to go something like this in between those two. Now, it doesn't say that it's differentiable everywhere, and it doesn't say that it is necessarily continuous everywhere. So this is concave up for all x, and what would we need to do then? We need to have something like that. So something like this, we've got our local maxima, we've got it concave up everywhere, and it remains positive for all x. As a second example, we're going to sketch this graph where the function of f of x is greater than 0. The derivative is greater than 0 for all points from f prime of x is greater than 0 from x greater than 1, so we need to label on 1 here. From -3 to 0. And that f prime of x equals 0 over the interval from 0 to 1. So from 0 to 1, we know that the derivative is 0. So I'm going to sketch that like this, a flat line. So that's taking care of this right here, that the derivative is 0. When x is greater than 1, the derivative is greater than 0. So that means we can have something like that. And from x and from -3 to 0, we also have it positive. So we should have something like that. If we wanted to continue, we could have that continue if we wanted. They don't specify it, but the things to note are the positive slope here, 0 slope, and then positive slope again. There's a bunch of problems on Khan Academy that I believe involve matching things together. We talked about those in class, so I don't feel a real need to go over examples of those. But if you want to ask more about them or go over some together, let me know.